Hello, this video will explain the fundamental theorem of calculus. If you were absent in class, then this is what we covered the last day. And we said that there are two parts to the theorem. This is one of the two parts. And so basically this is what we have. We have a function g of x, and the function g of x is equal to an integral. And we've never really had this before, where a function equals an integral, but these are called functions defined by an integral, or some people call them integral functions. A function defined by an integral. So then the things to pay attention to here are a couple. Notice that g is a function of x. So then g of x could be like 7x squared minus 2, square root of the sine of x, 1 over x cubed. G depends on x, so it's got x's in it. Now f is a different function, and f depends on t, some other variable. But they are linked by the integral, and the integral goes from a, which is a constant, to x, which is the variable that g depends on. And one way to think of it is if we drew a picture of it. Let me see. This is x, and this is y, and this is a function f, and I have my constant a, and so let's say x is a number here. Then let's think about what this integral is trying to tell us. The integral from a to x, it would mean, based on what we've seen so far in class, it's the area under the curve, isn't it? It'd be the area from a to x. And so whatever that number is, whatever the area happens to be, that would be the value for g of that x. Okay? So for instance, x could be, I don't know, a 3. Then if x is 3, then this becomes g of 3. And then you could see that it would have some sort of a value. The area could be 27 or 12, I don't know. But that would be g of that x value. Now, x is a variable, so it doesn't have to be 3. So you could have x somewhere else. This could be your x instead of those. And then this is now g of 3, everything here. Or x could be to the left of a, and then g of x would be the area from a to x. And that would actually be a negative value, wouldn't it, if you're going from right to left? And so you could see that for any x you choose, you have a different value associated with it. And isn't that really what a function is supposed to do? For every x, you get exactly one y. So the x could be here, and you get a certain value, a certain y. X could be farther down the line, and then g of x becomes a larger value. X could be to the left of a, and then g of x becomes a negative value. But every different x you choose will give you a different amount of area. And so then we call that a function. For every x, exactly one output. For every input, exactly one output. That's what's happening every time you select an x. And that's why we call g of x an integral function. It's a function that is defined by an integral. A function that is defined by how much area your integral was able to capture. Okay? So that's the physical explanation, or I should say the graphical explanation of functions defined by integrals. Now, let's go from the graphical to the analytical. So here's an actual integral function. G of x equals the integral from 3 to x of a function that is defined by a t variable. Notice how all the pieces connect. F of t, and this is an actual f of t function. It depends on t. However, g depends on x. And keep your eyes open. Now what we're going to try is, we're going to do this the long way without actually following the theorem, just to see why the theorem says what it says, okay? So then I'm going to try, what does the theorem say? The theorem says, if you take the derivative of g of x, okay? If you had g of x and you want g prime out of it, so here's a g of x function, it's defined by an integral, and I just want to know what would happen if I take the derivative. So let's try that. Now I'm going to do this the long way, so the first thing I'm going to try is, before I take the derivative of g of x, which is ultimately what I want, let me just take care of the integral. Let me do what it says to do. G of x says, take the integral of this function with respect to time. So what would the integral be for 4t? It'd be 4t squared divided by 2. Notice that I'm not taking the derivative, I'm just saying, since g of x says take the integral, then go ahead and take the integral. 4t squared over 2 minus 5t, and then this is evaluated from 3 to x. And I can still do some work with that, so I'll continue. G of x is equal to, now let me evaluate. The 4t squared over 2 becomes 2t squared over 2. But then I'm replacing upper limit minus lower limit, right? So it'll be 2x squared minus 5x. That's the upper limit, and me simplifying the fraction. Minus the lower limit 3, so it'd be 4 divided by 2, 2 times 3 squared minus 5 times 3. So there's g of x, upper limit minus lower limit. And then I could do a little more work with that. But remember, at the end, what I want to do is to find g prime of x. So then g of x here would be 2x squared minus 5x. And minus, let's see, that's 9 times 2, 18. And then that's minus 15, but with the other negative outside, it turns into plus 15. So g of x, 2x squared minus 5x minus 3. I think that's right. But now, what I want to do is to find g prime, right? G prime. So let's see, g prime of x. Now notice how after you take the integral, it truly is g of x, because there was a t associated with it, but the t was only good up until you evaluated the limits. And as soon as you try the upper limit, there's no more t. That's why g was called a function of x. A lot of students are confused by this. Why would you use x's and t's? Because at the end, g truly is just a function of x, if you were to take the integral. So then, now the derivative. G prime of x is equal to 4x minus 5. And what about the minus 3? Well, it goes away. So this is my result for g prime. And it took quite a few steps to get there, didn't it? Now look at what the theorem said. The theorem says, hey, if you want g prime, all you have to do is get the original function and replace that t with an x. And is that what happened here? Well, let's see, what was the original function? This was the original function, and the theorem says replace the t with x. Is that what happened? I think it did. It's 4t minus 5. My answer is 4x minus 5. The only thing that happened, the x became a t value. Or the t became an x, I'm sorry. So that's the theorem working for you. Now, what the theorem is also saying is, hey, look, don't take the integral and then evaluate the limits and then simplify and then take the derivative. We know what's going to happen. Every time you do this, you're just going to get back the original function, but the t's become x. And so the theorem just really saves a lot of time by saying, if you have a function g that is an an integral function, and you want to take the derivative, that was the key. You wanted to take the derivative. Then the derivative of the antiderivative is just the original function. That's another way to think about these. If you just kind of sound them out, g prime means take the derivative of whatever g is. And if g is an integral, another way of saying that is, if g is an antiderivative, then what would be the derivative of an antiderivative? Wouldn't those cancel out? And so the answer is yes, they cancel out. You just get your integrand back, but you have to do the substitution. Your t variable becomes x. And so what we're going to do from now on, we're never ever going to do this the long way. We are never going to actually take the integral, evaluate the limits, and then take the derivative, because that would be a waste of time. We're just going to follow the theorem and say, if you want the derivative of an integral function, you are just going to get the integrand, but my t variable becomes the x variable. Now, we didn't cover this in class, this example here. So spend some time going through it and make sure you understand how the theorem is trying to save us time, and also gain some trust in the theorem. It does work out. It does exactly what it says it would do. Okay. Now let me bring over another variant of the same theorem. And what this theorem says, instead of the integral from a to x, this is the integral from a to u. And by now you're used to having this standby variable or stand-in variable u, and u is a function of x. Okay, so you can still call this g of x instead of calling it g of u. Just know that u is a function of x and a is a constant. So this is like saying the integral from 5 to, I don't know, what's a function of x? 5x squared. So the integral from some number to sine x, the integral from 7 to the square root of x minus 1, the integral from negative 1/2 to tangent of x over 2. It's just a function of x, a remains a constant, g is a function of x because u is a function of x. And this t variable, as you've seen in the previous example, it doesn't really make much of a difference. It's going to be replaced by the u, the upper limit. And so then the theorem applied to this function says that if you wanted to take the derivative of the antiderivative of f of t dt, then you are going to get f, but t becomes u, and then by the chain rule, because you are taking a derivative, by the chain rule, after you do the substitution, you have to multiply by du dx, or u prime. And so you should memorize this part of the theorem just like you should memorize the original theorem. So this is a little variant of it. Now let's try an example of what I mean by this theorem. So here's my example, the derivative with respect to x of an integral. Now notice that the example doesn't say g of x is equal to the integral. They skip that step. They don't call this a function g of x. But they do say take the derivative with respect to x of that integral. So it's like saying, let's assume that this is your g of x. Take the derivative of g of x, or find g prime of x. But the bottom line is they want us to take the derivative of an antiderivative. Now notice the limits, because that's where the key lies. It's from 1 to x to the fourth. So would you say that it's part 1 or part 2 of the theorem? It's I shouldn't call it part 1 or part 2. It's the variant of the theorem, from a constant to a function of x, because x to the fourth, it's no x, but it's a function of x. So what does the theorem say to do? If you wanted to do this the long way, you would actually integrate secant and then take the derivative of that, evaluate the limits and then take the derivative. I'm not going to do that. I don't know, I don't even think I remember the integral of secant. What I'm going to do is I'm just going to follow the theorem. The theorem says your answer is going to be secant, but that t variable is going to become x to the fourth. We replace here just like we replace here. And then by the chain rule times 4x cubed. Notice that it's not the derivative of secant. It's just the derivative of u. Okay, so don't make it harder than it is. It's just u prime, and u was the upper limit. So don't try to do derivatives of integrands. It's just the derivative of u. And secant remains untouched. Secant of x to the fourth times 4x cubed. Well, what about the 1? Because nothing ever happened to the 1. Nothing is going to happen to the 1. Because if you were to do it the long way, that 1 is just a constant. And so when you evaluate it at a constant value and you take the derivative of the constant, you just get 0 for derivatives of constants. And so the only thing that matters now is the upper limit. And this would be the answer. Here's another example. We have a function y equals the integral from 1 over x to 7 of sine w dw. Now a few things that have changed, because they can always change things, and because labels are labels and you can label things whatever you want to label them. Instead of saying g of x, they just said y equals. But this is a function defined by an integral. You can see it clearly. And instead of using t dt, they're using sine of w dw. That w, that variable, can be whatever they want it to be. In the theorem, we have to use a variable. We say t, but it could be any variable they like. And so another thing that I noticed that has changed is, look at the limits. They put the constant on top. But when I look at the integral, the theorem had the constant on the bottom, from a to x, or from a to u. So then the first thing I would like to do is just change it so that it looks like my theorem. And I don't know if you remember, I hope you haven't forgotten, and I hope I've discussed this in class. I'm having second thoughts now. Maybe we didn't say this, but I think we did. There's a property that says the integral from a to b f of x dx is equal to the negative integral from b to a of the same f of x dx. Do you remember me saying this in class? I hope you do, and I hope I have said it in class. But basically what it says is, if you change the limits of integration, upper limit goes to the bottom and the lower limit goes to the top, then in essence you're going to get the same answer as before, but your answer is going to be negative. That kind of makes sense, because when you think of it, if you had a function and say you're going from a to b, well, it would be the area between the curve and the x-axis. Let's just say that area is 10. So your integral from a to b would be 10. But what if you change the limits and now you go from b to a? Well, the area hasn't changed. It'd still be 10. But because you are going from right to left, then now you have to stick a negative next to it. Okay? So basically, if you change the limits, if you swap them, upper and lower limit, then your integral is now negative. And I'm going to use that to take on this integral function. So let me first rewrite it and say y equals the negative integral from 7 to 1 over x of sine w dw. Whoa, dw. And see, now it fits the pattern that I had going here with my theorem from the constant to the function of x, from the constant to the function of x. And that negative is just a constant, so as long as I keep in mind that I have a negative out there, everything should be okay. Now, let me use the theorem. It says that all I need to do now is, if you want y prime, I'm still going to have a negative because that's like a constant coefficient, it's coming down. And for the integral, when I take the derivative of the antiderivative, I'm going to get sine. But that w is going to be replaced by the upper function 1 over x. And then by the chain rule, I'm going to multiply by the derivative of my upper limit, which is 1 over x. And how do you take the derivative of 1 over x? You can do the quotient rule, you can rewrite it so that it's x to the negative 1, and then do the power rule. But I've memorized this one because I've told you so many times that they like 1 over x. This is negative 1 over x to the second. That's the derivative of 1 over x. And that's what the theorem says to do. Replace t with u and then times u prime. Replace w with the function of x and then times the derivative of that function of x. And of course you can clean it up and say y prime is positive sine 1 over x. And if you want to, you can bring the 1 over x squared up front. And that is y prime. Or dy dx, whatever you want to call it. Now let me bring in another variation of the same theorem. And see, let's make this smaller, let's make that smaller. Let's see if that fits here. Oh. So this is the second variation of it. And what's the change you notice here? Yep, look at the limits. Now it's going from u sub 1 to u sub 2. And what do you think u sub 1 and u sub 2 are? Those are two functions of x. So this could be the integral from ln of x to 1 over x. This could be the integral from x cubed minus 2 to the square root of cosine x. Just any function of x you can think of, and then any other function of x you can think of for the upper limit. And g is still a function of x, and g is still defined by an integral. Okay? And by now, hopefully you see that this t variable is just a standby. It doesn't really do much. Some people call it a dummy variable. It's just there as a placeholder waiting to be substituted by u sub 2, and in this case also by u sub 1. So hopefully it's not much of a surprise that you see this result if you are to take the derivative. Notice that that's always been the thing. You have g, it's equal to an integral, and for some reason you want to take the derivative, which is not that far-fetched. We've been taking derivatives for a whole semester, right? So this is what people want to do to functions. They want to take derivatives. Notice the variation, g, and you want it g prime. And then the second variation, you have g function, and you want g prime. So now the second variation says you're still going to get the integrand because you're doing inverse operations here. You're taking the derivative of an antiderivative. So what would you expect? Operations are going to cancel each other out. And you'll get f of the upper limit, and then by the chain rule, times the derivative of the upper limit, because the upper limit is not x, but a function of x. And then minus f of the lower limit, and then by the chain rule again, times the derivative of the lower limit. Okay? So here's my fourth example. I want the integral from sine of x to cosine of x of this ln of 1 plus 2v with respect to v. And the instructions just say find the derivative. Notice that they've they've skipped a couple of things. They don't call g of x equal to this. They don't even bring in that other function g of x. They just say, hey, here's an integral, we want the derivative. So you can just pretend, hey, this integral is equal to a function, and I'm going to take the derivative of that function. And they don't specifically have to call it g of x or g of anything. Another thing, they're not using t as their standby variable, they're using v. But that should not concern you. They can call it whatever they want to call it. It's just a label. And at the end, this variable is going to go away anyway. So, can you see clearly that this, because of the limits, it doesn't really go with the original theorem, and it doesn't go with the first variation of the theorem. It actually matches the second variation of the theorem, which is if you have the integral from one function of x u sub 1 to another function of x u sub 2, then all we have to do is memorize the theorem and then do what it says to do. Now, you could actually do this the long way. You could take the integral of ln, because we know how to take the integral of ln of an argument, right? It'd be 1 over this argument and then divided by the derivative of that argument. And then you would have to evaluate from sine x to cosine x, and you would do upper limit minus lower limit. And you would actually get an expression, kind of lengthy expression. And then you could take the derivative of that. But let's not do that. It's going to take too long. Let's just follow what the theorem says. So we are going to have ln 1 plus 2. And then what do we plug in? The upper limit, cosine x. That's like saying f of u sub 2. But then by the chain rule times the derivative of, not the derivative of ln of the argument, just the derivative of the upper limit. So the derivative of cosine, negative sine x. And then the theorem continues, minus, go back to your integrand, write it up again. Write it down, I mean. And now v becomes sine, which was the lower limit. And then times the derivative of the lower limit, cosine x. So there you can see how the pieces correlate to each other. We're just doing a substitution and a chain rule that comes with that. And basically what we want to do is memorize the theorem, know that you have one general theorem, two variations of it, and then looking at the problem, you just have to figure out which of the three am I going to use and use it accordingly. So now here's a question from a textbook, and they give us a graph. Notice that they labeled the graph f of x. Actually, they called it f of t, because can you see that they called the axis t? And it's a piecewise function. And then here on top, they gave us a function g defined by an integral. So g of x is the integral from 0 to x. 0 is your constant. It could have been any other number. They chose 0. And g is a function of x, whereas f is a function of t. And then a few questions follow. This question I like because it kind of goes with what the AP test will ask you. These are the questions you can expect on a free response part of the test. So it's got A, B, C, D. The first part, I'm only going to answer a few questions from here, okay? So first part says evaluate g of 0, g of 1, g of 2, g of 3, g of 6. I'm just going to try a couple. So let's try g of 0, but before I try g of 0, let me rewrite g of x. G of x is equal to the integral from 0 to x f of t dt. Now g of 0 is what they want, g of 0. Well, this actually goes back to algebra 1. How do you evaluate functions when they give you a point? Basically all you do is you say, hey, x is 0. So replace x with 0. and then do the math. And that's exactly what we're going to do here, no different from before. So this actually becomes the integral from 0 to x, but x is now 0. F of, now t is a different variable, so this stays f of t dt. Only x becomes 0. And what does that mean, the integral from 0 to 0? Well, the integral means how much area you can accumulate. But if you go from 0 to itself, it doesn't let you gather any area. And so how much area can you have? Nothing really. From 0 to 0, all you have is a vertical line, and a vertical line does not contain any area. So that's g of 0. That was kind of simple enough. You just have to realize the property. If your upper limit and your lower limit are exactly the same number, then the integral has to be 0. There's no space, there's no room for any area. The next question says g of 1. G of 1. And that would be equal to the integral from 0 to 1. Now x becomes 1, f of t dt. And what would that equal? Well, let's see. I think I can make this a little larger. Oh, yes, I can make it a little larger. Okay. That's good enough. So the integral from 0 to 1 is telling me get the area from 0 to 1. And this is the area from 0 to 1. Just that piece. It's a rectangle, and the length of the rectangle or the base is 1, and the height is 2 by looking at their scale. And this is above the x-axis or the t-axis, so it's a positive 2. And that's g of 1. G of 1 is equal to 2. Now, the next question, g of 3. G of 3, well, that would equal the integral from 0 to 3 of f of t dt. And from 0 to 3, I already have from 0 to 1. I just need to gather more area. So how do I get it? I guess I can think of it as there's one trapezoid here, and then there is a triangle here. So a trapezoid and a triangle. Or some of you might say, hey, let's just make it, why not make it what I had before, one rectangle here, and then one rectangle here, and then a triangle here, and another triangle here. I don't know if you can see that color, probably not. It's a So one triangle there, one other triangle, two rectangles and two triangles. And if I do that, the area is going to be 2 for the first rectangle that I already had, plus my blue rectangle, that's another 2, isn't it? And then plus the green triangle, the base of it is 1, the height of it is 2, and it's base times height divided by 2 because it's a triangle. And then my last triangle, the one farthest to the right, that would be a base of 1, a height of 1, 2, 3, 4, and then divided by 2 because that's the formula for a triangle. So let's see, do you agree with that? 2 is my first rectangle, 2 is my second rectangle, and then 1 times 2 over 2, base 1, height 2 divided by 2, and then base 1, height 4 divided by 2. And we can get a total. That would just be 4 plus 1 plus 2. That is 7. I get 7. I hope you get the same answer as me. Okay? So that answers part A. G of 0, G of 1, G of 3. I skipped G of 2. You can try G of 2. You can try G of 6. Basically, all we have to do is replace x with the number that they gave us and think of the integral in terms of area. Now, when you get to g of 6, you have to be careful because now you have some area that falls below the x-axis, and that's going to make a difference, okay? So you're going to have to subtract areas as you go past 3. But I'm sure you can do that. Please make sure you understand how I got these numbers, the bases, the heights. It's all here. It's just simple geometry. And pay attention to the scale. They were very nice to us. Every little tick mark stands for 1 unit in the t direction and in the y direction. Okay, so now the second question, part B. On what interval is g increasing? Hey, have we answered that question before? Didn't we have a test on exactly that question? Intervals where g is increasing, or f, or whatever the function was. It's the same concept. All they're doing is they're adding an extra layer of complexity because now they want you to think of the fundamental theorem and use the fundamental theorem with whatever you've learned before to answer this question. So let me go back to what I know about what must be true if g is increasing. Okay? Can you help me with that? If g is increasing, then g prime has to be positive. Now this is from before. This is from a couple of weeks ago, or actually maybe a month ago. And if you still don't know that, come see me for tutoring. But I'm expecting everyone to know this fact. So g prime has to be positive. Now, do we have g prime? No, we have g of x. Let me write that again. What is g of x? It's the integral from 0 to x of f of t dt. So if I want to know g prime, we'll just take the derivative, g prime of x. And this is where the fundamental theorem helps us out, because the fundamental theorem says the derivative of the antiderivative is just f of, not t anymore, but x. Remember, the upper limit goes in there, and the lower limit makes no difference because when you take the derivative, it becomes 0. So g prime of x is equal to f of x. Now look, they call this function f. So now I know that the graph of f is exactly the same as the graph of, complete that sentence for me, g prime. Isn't that what we're saying? G prime is exactly the same as f. Now, believe it or not, on your free response AP exam, they want to see this equation somewhere. And if you make that connection, then you get a point. And actually, this will justify whatever follows. So very important, a very important line. G prime of x is equal to f of x. So then, if g prime is positive, if you want g to be increasing, g prime has to be positive. So now what we really want to know is, where is f positive? So g prime is greater than 0 whenever, that says whenever, f is greater than 0. And now this is an extremely easy question to answer. When is f greater than 0? Or when is f positive? F is positive whenever the graph of f is above the x-axis. So now look at it. When is the graph of f above the x-axis? Well, I can tell you right now that from 0 to, is that 3? From 0 to 3, that's when f is positive. So now we can answer the question, on what interval is g increasing? Complete statements, remember? G is increasing on 0 to 3. I'm going to use brackets because this is an increasing question. Some people might want to use parentheses because, actually, you know what? I should use bracket at 0, but I should use parentheses on 3 because right at 3, f is not positive, f is 0, and g prime would also be 0. Okay, so from 0 to 3, including 0, not including 3. And then so G is increasing on 0 to 3 because now this is important. G prime, which equals F, is positive on that interval. So you have to make that connection again. Okay? G prime is increasing on 0 to 3 because G prime, which is the same as F, is positive on that interval. And doesn't it refresh your memory on what we've been doing before about increasing and decreasing functions? Okay, so that's how we answer question B. Okay, the next question says, where does G have a maximum value? And I went back and forth when I read this question, because do they want to know where G attains a relative maximum? Is that the question? Or do they want to know where G attains its absolute maximum? Because they didn't use the words relative or absolute. When I read the question, the key to me is this here where it says a maximum. They used the article, is that an article? I think it is, a, instead of the maximum. And so to me, a maximum is one of many, or several, or a few. And if they had said the maximum, then it means the absolute. Or if they had said, where does G attain its maximum value, then to me that sounds like the absolute, the highest possible point. But this article that they used, a maximum value, it makes it sound like just a relative, one of many maxima. So I'm going to answer both questions. I'm going to say this is the relative, and then I'm also going to say this is the absolute, okay? So first, I really do think they want to know just the relative. Where does G have a relative maximum? Okay, so what must be true about G prime if you wanted to have a relative maximum? And why am I asking things about G prime if the question was about G of x? Because remember, you have the graph of G prime. This is the graph of G prime. So whenever they ask a question about G, we have to translate it so that it's in terms of what they gave us, which is G prime. And basically this is what we reviewed a few weeks ago. So if you want G to have a maximum, that's a maximum right there. Then think about G prime. What are the slopes doing? Well, it goes from a positive slope to a zero slope to a negative slope. So then G prime must change from positive to negative. Now this is not part of my answer. This is just like me letting you know my train of thought. G must change from positive to negative. So it's like scratch work, I guess. And so then where does that happen? Now this makes the question very simple. And now it's almost laughable that they would ask this kind of question. But there's a lot of thinking that goes behind it. So where does G prime go from positive to negative? Well, again, this is the graph of G prime. This is above the t-axis, so that's positive G. This is below the t-axis, so that's a negative G prime. Did I say G? G prime. Positive G prime, negative G prime. And this is where it changes, where G prime changes from positive to negative. So I'm ready to answer the question about a relative maximum. Then I would say G attains a relative maximum at t equals, it is the t-axis, right? Should I say t or x? Well, the question is in terms of x. I'm sorry, the question is in terms of G, and G is a function of x. I don't think it matters whether you say x or 3. But I'm going to say t equals 3. I guess you could say x if you want to. G attains a relative maximum at t equals 3 because and this is important again, because G prime, which is equal to f, changes from positive to negative at t equals 3. Now, if you're going to use t, then make sure you use t again for the second time. Don't switch between t and x. Okay, so this is my answer if this was about a relative maximum. Now, I think I now understand why they're not asking about an absolute. Because if they wanted to ask you about an absolute, they should have given you the endpoints. Now, the graph gives you endpoints, but the question doesn't give you endpoints. But on the AP test, don't worry, they'll be more careful about things. This is a question from a textbook. The AP exam is a little more, they revise their questions a lot. So let me answer the question in terms of the AP exam, okay? Let me erase this and come back with another question. So this is what the question would look like if they wanted the absolute maximum. Where does G attain its maximum value on 0 to 7, the closed interval 0 to 7? So they do a couple of things. Now they're giving you endpoints, and by saying its maximum value, it's very clear to me when I read that they mean the absolute maximum. Would you agree? Okay, so what do? Same as before, you want to maximize G. So the primary equation is G of x. And then what are we going to do? We're going to take the derivative of the primary and set it equal to 0. And where does that happen? That happens whenever f is equal to 0. And where does that happen? When t is equal to 3. Or now I'm going to say x, because I said g prime of x. So x is equal to 3. Now again, if this is one single question, for every single part, A, B, C, D, I keep using the same. If you're going to use x, then keep using x for the rest of the questions. If you're going to use t, keep using t for the rest of the questions. Don't switch back and forth. I don't think they'll penalize you heavily for that, but we don't want to take any chances. So when x is equal to 3, and what is this I found? This is the critical value. And what else do we have? We have endpoints. What are the endpoints? X is equal to 0 and x is equal to 7. So then what do? We evaluate the critical value and evaluate the endpoints, okay? So I'm going to start with G of 0 because I'm going left to right. So let me just clarify. I'm going to try 0, I'm going to try 7, and I'm going to try 3. And the absolute maximum has to be either from the critical value or from the endpoints, right? So let me start again left to right. I'm going to try G of 0. And how do I figure out G of 0? Well, remember, G of x was this integral equation, so you just have to replace x with 0. So G of 0 is going to be the integral from 0 to 0 of f of x. And we know what that is. I'm sorry, not f of x. F of t dt. And we know what that will be, right? From 0 to 0, the integral is 0. Well, there you go. You just evaluated one of the endpoints. Now let me go and evaluate G of 3. G of 3 is the integral from 0 to 3, f of t dt. But hey, didn't we have that already from before? G of 3 was, I think it was 7, right? And it was one of the first things we evaluated, G of 3. And it was the 2 rectangles plus the 2 triangles. And now, G of 7. Now, the thing about G of 7, can you see that I don't really have to get the area? But if you wanted to, you could. You could go ahead and get the area for that piece right there. And then it's a trapezoid. Or you can make it 2 triangles and a rectangle. But basically, if G of 7 is the integral from 0 to 7 of f of t dt, wouldn't that be less than G of 3? Because now you have a negative, I don't want to say negative area. Now you have area below the x-axis. So then we can just say this is less than g of 3. And trust me that you don't really have to justify that. When they see that statement, they'll know what you mean. And unless you don't want to say this and you actually want to go figure out the area and then subtract it from the 7, because remember this is area below the x-axis. So if you want to take a little more time and get the area and then subtract it from the previous area that was 7, then you can go ahead and do that. I'm just going to say, hey, look, if I go below the x-axis, I'm going to subtract that area. And if I'm going to subtract the area, whatever value I get, it's going to be less than 7. Okay? So then I think I found my absolute maximum. So let me answer the question now. The question was, where does G attain its absolute maximum? And the answer is G attains its absolute maximum at x equals, that's my at sign, at x equals 3. And you don't have to justify it with a statement because all the work you've shown is how you justify this. This is, again, a very typical question of the AP exam, those first 3 questions. I'm not going to answer letter D. Letter D says to sketch a graph. It's going to take a little longer. This video is pretty long by now, so I'm just going to leave it at this. The graph of G, all you do is put everything together from A, B, and C, plot a few points, because you have quite a few points. You have 5 points from the first part. You know where the maximum is. You know that it's an absolute max. You know where G is increasing. You should know where G is decreasing. And you put it all together to create a possible sketch of G of x. Okay? So please make sure you spend some time looking at the example. Make sure you understand what happened here. And hopefully you can see that nothing has changed, really. The only difference I see is that when we evaluate over here, now it's a little different because we are not going to a function and just doing algebra. Now to evaluate the function, we have to figure out what the integral is, but then thinking about areas will help you figure out the expression for G of 0, G of 3, and G of 7. And in a way, it's easier than before. Before you had to cube something, multiply, take the square root. Now we're just saying to evaluate G of 0, G of 3, and G of 7, think about the area. And so if it's a piecewise function, the areas are quite easy to calculate. We covered a lot of material in the video. It's the longest video ever. But hopefully you understand what's happening, especially if you were not there with us when we covered the fundamental theorem. And play it back as many times as you want to. Make sure you understand how to answer questions like this one here from the textbook number 3. It's not from your textbook, it's a different one, but it's a good example. Okay, let me give you the assignment that I'm expecting you to turn in from the AP packet. And you are going to have to do it on a separate sheet of paper. Okay, so I'm going to give you some numbers from your AP packet. And I think I gave you like a repeated page in that packet. So don't worry about that. But please write down the following numbers because this is the homework that I am expecting you to turn in to me by Monday. Hold on. So this is the assignment that I want you to have with you by Monday. You should have started on a few of these. So there's a chance you've worked out, hopefully maybe halfway through it or more. And if you haven't started, then shame on you and you have 2 days to complete it. And this is an important homework. It's very important. And these questions, trust me, it's exactly what you are going to see the day of the AP test. And if you know how to answer these questions, then there's very little you cannot do. So make sure you invest your time working out these problems, okay? And in class, I'll answer a few questions, but we do have new things that we need to cover. And so please try as many as you can from here. If you get stuck, then I guess go back to the notes, go back to the video. I'll have another video for you tomorrow. Or if this is Saturday, then you'll get another video Saturday or Sunday. And maybe I address your questions in those videos. But do this on a separate sheet of paper, okay? And you're gonna have to rewrite the questions. Some of them are kind of simple to rewrite. If you have graphs, just do like a quick sketch, or if you want to use graph paper and be more detailed about the graph, but on many of these, the graph is important. The absolute value questions, you're gonna have to graph before you find the integral, like I showed you in the previous video. And that is it. I'll expect another video again Saturday or Sunday before we come back, and have fun.